Hello, this is Todd Booth, and I'll be covering Chapter 2, Symmetric Encryption and Message Confidentiality. Again, these slides are from the book. So this chapter begins with a look at a general model for the symmetric encryption process. This will enable us to understand the concept within which the algorithms are used. Then we will look at three important block encryption algorithms, DES, triple DES, and AES. This is followed by discussion of random and pseudo-random number generation. Next, the chapter introduces symmetric stream encryption and describes the widely used stream cipher RC4. Finally, we look at the important topic of block cipher modes of operation. So this is an interesting quote in the book. I'll go ahead and read it. I have solved other ciphers of an obtrusiveness 10,000 times greater. Circumstances and a certain bias of mind have led me to take interest in such riddles, and it may well be doubted whether human ingenuity can construct an enigma of the kind of which human ingenuity may not by proper application resolve. So that's an interesting one. So symmetric encryption, also referred to as conventional encryption, secret key or single key encryption, was the only type of encryption in use prior to the development of public key encryption in the late 1970s. It remains by far the most widely used of the two types of encryption. And here we have some basic terminology that we're going to be using throughout the course. We have plaintext, ciphertext, cipher, key, encipher, decipher, cryptography, cryptanalysis, cryptology. I won't read through all the definitions, and we will cover them in the next slide, most of them. So a symmetric encryption scheme has 5 ingredients. Plain text, this is the original message or data that is fed into the algorithm as input. The encryption algorithm performs various substitutions and transformations on the plain text. Secret key, the secret key is also input to the algorithm. The exact substitutions and transformations performed by the algorithm depend on the key. Ciphertext, this is the scrambled message produced as output. It depends on the plain text and the secret key. For a given message, 2 different keys will produce 2 different ciphertexts. Decryption algorithm, this is essentially the encryption algorithm run in reverse. It takes the ciphertext and the same secret key and produces the original plaintext. There are 2 requirements for secure use of symmetric encryption. We need a strong encryption algorithm. At a minimum, we would like the algorithm to be such that an opponent who knows the algorithm and has access to one or more of the ciphertexts would be unable to decipher the ciphertext or figure out the key. This requirement is usually stated in a stronger form. The opponent should be unable to decrypt ciphertext or discover the key, even if he or she is in possession of a number of ciphertexts together with the plaintext that produced each ciphertext. 2. Sender and receiver must have obtained copies of the secret key in a secure fashion and must keep the key secure. If someone can discover the key and knows the algorithm, all communication using this key is readable. It is important to note that the security of symmetric encryption depends on the secrecy of the key, not the secrecy of the algorithm. That is, it is assumed that it is impractical to decrypt a message on the basis of the ciphertext plus knowledge of the encryption-decryption algorithm. In other words, we do not need to keep the algorithm secret. We need to keep only the key secret. This feature of symmetric encryption is what makes it feasible for widespread use. The fact that the algorithm need not be kept secret means that manufacturers can and have developed low-cost chip implementations of data encryption algorithms. These chips are widely available and incorporated into a number of products. With the use of symmetric encryption, the principal security problem is maintaining the secrecy of the key. Cryptographic systems are generally classified along three independent dimensions. 1. The type of operations used for transforming plain text to ciphertext. All encryption algorithms are based on two general principles. Substitution, in which each element in the plain text, bit, letter, group of bits or letters, is mapped into another element. And transposition, in which elements in the plain text are rearranged. The fundamental requirement is that no information be lost, i.e., that all operations be reversible. Most systems, referred to as product systems, involve multiple stages of substitutions and transpositions. 2. The number of keys used. If both sender and receiver use the same key, the system is referred to as symmetric, single key, secret key, or conventional encryption. If the sender and receiver each use a different key, the system is referred to as asymmetric, two-key, or public key encryption. 3. The way in which the plain text is processed. A block cipher processes the input one block of elements at a time, producing an output block for each input block. A stream cipher processes the input elements continuously, producing output one element at a time as it goes along. The process of attempting to discover the plaintext or key is known as cryptanalysis. The strategy used by the cryptanalyst depends on the nature of the encryption scheme and the information available to the cryptanalyst. The figure summarizes the various types of cryptanalytic attacks based on the amount of information known to the cryptanalyst. The most difficult problem is presented when all that is available is the ciphertext only. In some cases, not even the encryption algorithm is known, but in general, we can assume that the opponent does know the algorithm used for encryption. One possible attack under these circumstances is the brute force approach of trying all possible keys. If the key space is very large, this becomes impractical. Thus, the opponent must rely on an analysis of the ciphertext itself, generally applying various statistical tests to it. To use this approach, the opponent must have some general idea of the type of plaintext that is concealed, such as English or French text, or an exe file, a Java source listing, an accounting file, and so on. The ciphertext-only attack is the easiest to defend against because the opponent has the least amount of information to work with. In many cases, however, the analyst has more information. The analyst may be able to capture one or more plaintext messages as well as their encryptions. Or the analyst may know that certain plaintext patterns will appear in a message. For example, a file that is encoded in the PostScript format always begins with the same pattern. Or there may be a standardized header or banner to an electronic funds transfer message, and so on. All of these are examples of known plaintext. With this knowledge, the analyst may be able to deduce the key on the basis of the way in which the known plaintext is transformed. Closely related to the known plaintext attack is what might be referred to as a probable word attack. If the opponent is working with the encryption of some general message, he or she may have little knowledge of what is in the message. However, if the opponent is after some very specific information, then parts of the message may be known. For example, if an entire accounting file is transmitted, the opponent may know the placement of certain keywords in the header of the file. As another example, the source code for a program developed by a corporation might include a copyright statement in some standardized position. If the analyst is able to somehow get to the source system to insert into the system a message chosen by the analyst, then a chosen plaintext attack is possible. In general, if the analyst is able to choose the message to encrypt, the analyst may deliberately pick patterns that can be expected to reveal the structure of the key. In the table are listed two other types of attack: chosen ciphertext and chosen text. They are less commonly employed as cryptanalytic techniques, but are nevertheless possible avenues of attack. Cryptanalysis. Only relatively weak algorithms fail to withstand a ciphertext-only attack. Generally, an encryption algorithm is designed to withstand a known plaintext attack. An encryption scheme is computationally secure if the ciphertext generated by the scheme meets one or both of the following criteria. The cost of breaking the cipher exceeds the value of the encrypted information. The time required to break the cipher exceeds the useful lifetime of the information. Unfortunately, it is very difficult to estimate the amount of effort required to cryptanalyze ciphertext successfully. However, assuming that there are no inherent mathematical weaknesses in the algorithm, then a brute force method can be applied. A brute force attack involves trying every possible key until an intelligible translation of the ciphertext into plaintext is obtained. On average, half of all possible keys must be tried to achieve success. That is, if there are X different keys, on the average, an attacker would discover the actual key after X divided by 2 tries. It is important to note that there is more to a brute force attack than simply running through all possible keys. Unless known plaintext is provided, the analyst must be able to recognize plaintext as plaintext. If the message is just plaintext in English, then the result pops out easily, although the task of recognizing English would have to be automated. If the text message has been compressed before encryption, then recognition is more difficult. And if the message is some more general type of data, such as a numerical file, and this has been compressed, the problem becomes more difficult to automate. Thus, to supplement the brute force approach, some degree of knowledge about the expected plaintext is needed, and some means of automatically distinguishing plaintext from garble is also needed. Many symmetric block encryption algorithms, including DES, have a structure first described by Horst Festel of IBM in 1973 and shown in this diagram. The inputs to the encryption algorithm are a plaintext block of length 2W bits and a key K. The plaintext block is divided into two halves, the left half and the right half. The two halves of the data pass through n rounds of processing and then combine to produce the ciphertext block. Each round I has as input the left of I-1 and the right of I-1 derived from the previous round, as well as a subkey derived from the overall key. In general, the subkey ki are different from k and from each other and are generated from the key by a subkey generation algorithm. In the figure, 16 rounds are used, although any number of rounds could be implemented. The right-hand side of the figure shows the decryption process. All rounds have the same structure. A substitution is performed on the left half of the data. This is done by applying a round function f to the right half of the data and then taking the exclusive OR, XOR, of the output of that function and the left half of the data. The round function has the same general structure for each round, but is parameterized by the round subkey ki. Following this substitution, a permutation is performed that consists of the interchange of the two halves of the data. The Feastal structure is a particular example of the more general structure used by all symmetric block ciphers. In general, a symmetric block cipher consists of a sequence of rounds, with each round performing substitutions and permutations conditioned by a secret key value. The exact realization of a symmetric block cipher depends on the choice of the following parameters and design features. Block size. Larger block sizes mean greater security, all other things being equal, but reduced encryption-decryption speed. A block size of 128 bits is a reasonable trade-off and is nearly universal among recent block cipher designs. Key size. Larger key size means greater security, but may decrease encryption-decryption speed. The most common key length in modern algorithms is 128 bits. Number of rounds. The essence of symmetric block cipher is that a single round offers inadequate security, but that multiple rounds offer increasing security. A typical size is from 10 to 16 rounds. Subkey generation algorithm. Greater complexity in this algorithm should lead to greater difficulty of crypt analysis. Round function. Again, greater complexity generally means greater resistance to crypt analysis. There are two other considerations in the design of a symmetric block cipher. Fast software encryption-decryption. In many cases, encryption is embedded in applications or utility functions in such a way as to preclude a hardware implementation. Accordingly, the speed of execution of the algorithm becomes a concern. Ease of analysis. Although we would like to make our algorithms as difficult as possible to cryptanalyze, there is great benefit in making the algorithm easy to analyze. That is, if the algorithm can be concisely and clearly explained, it is easier to analyze that algorithm for cryptanalytic vulnerabilities and therefore develop a higher level of assurance as to its strength. DES, for example, does not have an easily analyzed functionality. Symmetric block encryption algorithms. The most commonly used symmetric encryption algorithms are block ciphers. A block cipher processes the plaintext input in fixed size blocks and produces a block of ciphertext of equal size for each plain text block. This section focuses on the three most important symmetric block ciphers: the data encryption standard, triple DES, and the advanced encryption standard. Data encryption standard, DES. The most widely used encryption scheme is based on the data encryption standard, DES, issued in 1977 as USA Federal Information Processing Standard 46, FIPS 46, by the National Bureau of Standards, now known as the National Institute of Standards and Technology, NIST, in the USA. The algorithm itself is referred to as the Data Encryption Algorithm, DEA. DES algorithm. The plain text is 64 bits in length and the key is 56 bits in length. The longer plain text amounts are processed in 64-bit blocks. The DES structure is a minor variation of the Feistel network shown in Figure 2.2 before. There are 16 rounds of processing. From the original 56-bit key, 16 subkeys are generated, one of which is used for each round. The process of decryption with DES is essentially the same as the encryption process. The rule is as follows. Use the ciphertext as input to the DES algorithm, but use the subkey Ki in reverse order. That is, use K16 on the first iteration, K15 on the next, and so forth. Concerns about the strength of DES fall into two categories: concerns about the algorithm itself and concerns about the use of a 56-bit key. The first concern refers to the possibility that cryptanalysis is possible by exploiting the characteristics of the DES algorithm. Over the years, there have been numerous attempts to find and exploit weaknesses in the algorithm, making DES the most studied encryption algorithm in existence. Despite numerous approaches, no one has thus far succeeded in discovering a fatal weakness in DES. A more serious concern is key length. With a key length of 56 bits, there are 2 to the 56th possible keys, which is approximately 7.2 times 10 to the 16th keys. Thus, on the face of it, a brute force attack appears impractical. Assuming that on the average, half the key space has to be searched, a single machine performing DES encryption per microsecond would take more than 1,000 years to break the cipher. However, the assumption of one encryption per microsecond is overly conservative. DES finally and definitively proved insecure in July of 1998, when the Electronic Frontier Foundation, EFF, announced that they had broken a DES encryption using a special purpose DES cracker machine that was built for less than $250,000 US. The attack took less than 3 days. The EFF has published a detailed description of the machine, enabling others to build their own cracker. And of course, hardware prices will continue to drop as speeds increase, making DES virtually worthless. With current technology, it is not even necessary to use special purpose-built hardware. Rather, the speed of commercial off-the-shelf processors threaten the security of DES. A paper from Seagate Technology suggests that a rate of 1 billion key combinations per second is reasonable for today's multi-core computers. Recent offerings confirm this. Both Intel and AMD now offer hardware-based instructions to accelerate the use of AES. Tests run on a contemporary multi-core Intel machine resulted in an encryption rate of about 500,000,000. Another recent analysis suggests that with contemporary supercomputer technology, a rate of 10 to the 13 encryptions per second is reasonable. Considering these results, this table shows how much time is required for a brute force attack for various key sizes. As can be seen, a single PC can break desks in about half a year. If multiple PCs work in parallel, the time is drastically shortened. And today's supercomputers should be able to find a key in about an hour. Key sizes of 128 bits or greater are effectively unbreakable using simply a brute force approach. Even if we manage to speed up the attacking system by a factor of 1 trillion, it would still take over 100,000 years to break a code using a 128-bit key. Triple DES was first standardized for use in financial applications in ANSI in 1985. Triple DES was incorporated as part of the data encryption standard in 1999 with the publication of FIPS 46-3. Triple DES uses 3 keys and 3 executions of the DES algorithm. The function follows an encrypt, decrypt, encrypt sequence. There is no cryptographic significance to the use of the decryption for the second stage of triple DES encryption. Its only advantage is that it allows users of triple DES to decrypt data encrypted by users of the older single DES. With 3 distinct keys, triple DES has an effective key length of 168 bits. Triple DES guidelines. So FIPS 46-3 includes the following guidelines for triple DES. Triple DES is the FIPS approved symmetric encryption algorithm of choice. The original DES, which uses a single 56-bit key, is permitted under the standard for legacy systems only. New procurements should support triple DES. Government organizations with legacy DES systems are encouraged to transition to triple DES. It is anticipated that triple DES and the Advanced Encryption Standard AES will coexist as FIPS-approved algorithms, allowing for a gradual transition to AES. It is easy to see that triple DES is a formidable algorithm because the underlying cryptographic algorithm is DAA. Triple DES can claim the same resistance to cryptanalysis based on the algorithm as is claimed for DEA. Furthermore, with a 168-bit key length, brute force attacks are effectively impossible. Ultimately, AES is intended to replace triple DES, but this process will take a number of years. NIST anticipates that triple DES will remain an improved algorithm for U.S. government use for the foreseeable future. The principal drawback of triple DES is that the algorithm is relatively sluggish in software. The original DEA was designed for mid-1970s hardware implementation and does not produce efficient software code. Triple DES, which has 3 times as many rounds as DEA, is correspondingly slower. A secondary drawback is that both DEA and triple DES use a 64-bit block size. For reasons of both efficiency and security, a larger block size is desirable. Because of these drawbacks, triple-DES is not a reasonable candidate for long-term use. As a replacement, NIST in 1997 issued a call for proposals for a new advanced encryption algorithm, which should have a security strength equal to or better than triple-DES and significantly improved efficiency. In addition to these general requirements, NIST specified that AES must be a symmetric block cipher with a block length of 128 bits and support for key lengths of 128, 192, and 256 bits. Evaluation criteria included security, computational efficiency, memory requirements, hardware and software suitability, and flexibility. In a first round of evaluation, 15 proposed algorithms were accepted. A second round narrowed the field to 5 algorithms. NIST completed its evaluation process and published a final standard, FIPS-Pub 197. That was done in November of 2001. NIST selected Rindahl as the proposed AES algorithm. The two researchers who developed and submitted Rindahl for the AES are both cryptographers from Belgium, Dr. Joan Damon and Dr. Vincent Raymond. AES uses a block length of 128 bits and a key length that can be 128, 192, or 256 bits. In the description of this section, we assume a length of 128 bits, which is likely to be one of the most commonly implemented. The input to the encryption and decryption algorithms is a single 128-bit block. In FIPS-Pub 197, this block is depicted as a square matrix of bytes. This block is copied into the state array, which is modified at each stage of encryption or decryption. After the final stage, state is copied to an output matrix. Similarly, the 128-bit key is depicted as a sequence of square matrix or bytes. This key is then expanded into an array of key schedule words. Each word is 4 bytes, and the total key schedule is 44 words for the 128-bit key. The ordering of bytes within a matrix is by columns. So, for example, the first 4 bytes of 128-bit plaintext input to the encryption cipher occupy the first column of the in matrix. The second 4 bytes occupy the second column, and so on. Similarly, the first 4 bytes of the expanded key, which form a word, occupied the first column of the W matrix. Four different stages are used: 1 of permutation and 3 of substitution. Substitute bytes uses a table referred to as next SBox to perform a byte-by-byte substitution of the block. Shift rows, a simple permutation that is performed row by row. Mix columns, a substitution that alters each byte in a column as a function of all of the bytes in the column. Add round key, a simple bitwise XOR of the current block with a portion of the expanded key. This diagram depicts the structure of a full encryption round. Random and pseudorandom numbers. Random numbers play an important role in the use of encryption for various network security applications. We provide an overview in this section. The topic is examined in more detail in Appendix E. A number of network security algorithms based on cryptography make use of random numbers. For example, generation of keys for the RSA public key encryption algorithm, described in Chapter 3, and other public key algorithms. Generation of a stream key for symmetric stream cipher, discussed in the following section. Generation of a symmetric key for use as a temporary session key. This function is used in a number of networking applications, such as transport layer security, Wi-Fi, email security, and IP security. In a number of key distribution scenarios, such as Kerberos, random numbers are used for handshaking to prevent replay attacks. These applications give rise to two distinct and not necessarily compatible requirements for a sequence of random numbers: randomness and unpredictability. Traditionally, the concern in the generation of a sequence of allegedly random numbers has been that the sequence of numbers be random in some well-defined statistical sense. The following criteria are used to validate that a sequence of numbers is random. Uniform distribution. The distribution of bits in the sequence should be uniform. That is, the frequency of occurrence of ones and zeros should be approximately the same. Independence. No one subsequence of the sequence can be inferred from the others. Although there are well-defined tests for determining that a sequence of random numbers matches a particular distribution, such as the uniform distribution, there is no such test to prove independence. Rather, a number of tests can be applied to demonstrate if a sequence does not exhibit independence. The general strategy is to apply a number of such tests until the confidence that independence exists and is sufficiently strong. Unpredictability. In applications such as reciprocal authentication and session key generation, the requirement is not so much that the sequence of numbers be statistically random, but that the successive members of the sequence are unpredictable. With true random sequences, each number is statistically independent of other numbers in the sequence, and therefore unpredictable. However, as is discussed shortly, true random numbers are not always used. Rather, sequences of numbers that appear to be random are generated by some algorithm. In this latter case, care must be taken that an opponent not be able to predict future elements of the sequence on the basis of earlier elements. Cryptographic applications typically make use of algorithmic techniques for random number generation. These algorithms are deterministic and therefore produce sequences of numbers that are not statistically random. However, if the algorithm is good, the resulting sequences will pass many reasonable tests of randomness. Such numbers are referred to as pseudo-random numbers. You may be somewhat uneasy about the concept of using numbers generated by a deterministic algorithm as if they were random numbers. Despite what might be called philosophical objections to such a practice, it generally works. That is, under most circumstances, pseudo-random numbers will perform as well as if they were random for a given use. The phrase "as well as" is unfortunately subjective, but the use of pseudo-random numbers is widely accepted. The same principle applies in statistical application, in which a statistician takes a sample of a population and assumes that the results will be approximately the same as if the whole population were measured. The figure contrasts a true random number generator, TRNG, with two forms of pseudo-random number generators. A TRNG takes as input a source that is effectively random. The source is often referred to as an entropy source. In essence, the entropy source is drawn from the physical environment of the computer and could include things such as keystroke timing patterns, disk electrical activity, mouse movements, and instantaneous values of the system clock. The source or combination of sources serves as input to an algorithm that produces random binary output. A TRNG may simply involve conversion of an analog source to a binary output. The TRNG may involve additional processing to overcome any bias in the source. In contrast, a PRNG takes as input a fixed value called the seed and produces a sequence of output bits using a deterministic algorithm. Typically, as shown in the figure, there is some feedback path by which some of the results of the algorithm are fed back as input as additional output bits are produced. The most important thing to note is that the output bit sequence is determined solely by the input value or values, so that an adversary who knows the algorithm and the seed can reproduce the entire bit stream. The figure shows two different forms of PRNGs based on application. Pseudorandom number generator. An algorithm that is used to produce an open-ended sequence of bits is referred to as a PRNG. A common application for an open-ended sequence of bits is as input to a symmetric stream cipher, as discussed in the following section. Pseudorandom function, PRF. A PRF is used to produce a pseudorandom string of bits of some fixed length. Examples are symmetric encryption keys and nonces. Typically, the PRF takes as input a seed plus some context-specific values, such as a user ID or an application ID. A number of examples of PRFs will be seen throughout this book. Other than the number of bits produced, there is no difference between a PRNG and a PRF. The same algorithms can be used in both applications. Both require a seed and both must exhibit randomness and unpredictability. Furthermore, a PRNG application may also employ context-specific input. Algorithm design. Cryptographic PRNGs have been the subject of much research over the years, and a wide variety of algorithms have been deployed. These fall roughly into two categories. Purpose-built algorithms. These are algorithms designed specifically and solely for the purpose of generating pseudorandom bit streams. Some of these algorithms are used for a variety of PRNG applications. Several of these are described in the next section. Others are described specifically in this section. The design is specifically for the use in a stream cipher. The most important example of the latter is RC4, described in the next section. Algorithms based on existing cryptographic algorithms. Cryptographic algorithms have the effect of randomizing input. Indeed, this is a requirement of such algorithms. For example, if a symmetric block cipher produced ciphertext that had certain regular patterns in it, it would aid in the process of cryptanalysis. Thus, cryptographic algorithms can serve as the core of PRNGs. Three broad categories of cryptographic algorithms are commonly used to create PRNGs: symmetric block ciphers, asymmetric ciphers, hash functions, and message authentication codes. Any of these approaches can yield a cryptographically strong PRNG. A purpose-built algorithm may be provided by an operating system for general use. For applications that are already using certain cryptographic algorithms for encryption or authentication, it makes sense to reuse the same code for the PRNG. Thus, all of these approaches are in common use. A typical stream cipher encrypts plaintext 1 byte at a time, although a stream cipher may be designed to operate on 1 bit at a time or on units larger than a byte at a time. The figure is a representative diagram of stream cipher structure. In this structure, a key is input to a pseudo-random bit generator that produces a stream of 8-bit numbers that are apparently random. The pseudo-random stream is unpredictable without knowledge of the input key and has an apparently random character. The output of the generator, called a key stream, is combined 1 byte at a time with the plaintext stream using the bitwise exclusive OR operation. Stream cipher design considerations. Kuma 97 reference lists the following important design considerations for a stream cipher. The encryption sequence should have a large period. A pseudo-random number generator uses a function that produces a deterministic stream of bits that eventually repeats. The longer the period of repeat, the more difficult it will be to do the crypt analysis. 2. The key stream should approximate the properties of a true random number stream as close as possible. For example, there should be an approximately equal number of ones and zeros. If the key stream is treated as a stream of bytes, then all of the 256 possible byte values should appear approximately equally often. The more random appearing the stream is, the more randomized the ciphertext is, making crypt analysis more difficult. Note from Figure 2.7 that the output of the pseudo-random number generator is conditioned on the value of the input key. To guard against brute force attacks, the key needs to be sufficiently long. The same considerations as applied to block ciphers are valid here. Thus, with current technology, a key length of at least 128 bits is desirable. RC4 algorithm. RC4 is a stream cipher designed in 1987 by Ron Rivest for RSA security. It is a variable key size stream cipher with byte-oriented operations. The algorithm is based on the use of a random permutation. Analysis shows that the period of the cipher is overwhelmingly likely to be greater than 10,100. 8 to 16 machine operations are required per output byte, and the cipher can be expected to run very quickly in software. RC4 is used in the Secure Sockets Layer Transport Layer Security SSL/TLS standards that have been defined for communication between web browsers and servers. It is also used in the Wired Equivalent Privacy WEP protocol and the newer Wi-Fi Protected Access protocol that are part of the IEEE 802.11 wireless LAN standard. RC4 was kept as a trade secret by RSA Security. In September 1994, the RC4 algorithm was anonymously posted on the internet on the Cypherpunks Anonymous Remailers list. The RC4 algorithm is remarkably simple and quite easy to explain. A variable length key of from 1 to 256 bytes, which is 8 to 2048 bits, is used to initialize a 256 byte state vector S. with elements S0, S1, etc. to S255. At all times, S contains a permutation of all 8-bit numbers from 0 through 255. For encryption and decryption, a byte K is generated from S by selecting one of the 255 entries in a systematic fashion. As each value of K is generated, the entries in S are once again permuted. A number of papers have been published analyzing methods of attacking RC4. None of these approaches is practical against RC4 with a reasonable key size, such as 128 bits. A more serious problem is reported in FLU H01 for reference. The authors demonstrate that the web protocol intended to provide confidentiality on 802.11 wireless LAN networks is vulnerable to a particular attack approach. In essence, the problem is not with RC4 itself, but the way in which keys are generated for use as input to RC4. This particular problem does not appear to be relevant to other applications using RC4 and can be remedied in web by changing the way in which the keys are generated. This problem points out the difficulty in designing a secure system that involves both cryptographic functions and protocols that make use of them. So here's a figure which illustrates the RC4 logic. Cipher block modes of operation. A symmetric block cipher produces one block of data at a time. In the case of DES and triple DES, the block length is B equals 64 bits. For AES, the block length is B equals 128 bits. For longer amounts of plaintext, it is necessary to break the plaintext into B blocks of data. Padding the last block is necessary. To apply a block cipher in a variety of applications, 5 modes of operations that have been defined by NIST, the 5 modes are intended to cover virtually all of the possible applications of encryption for which a block cipher could be used. These modes are intended for use with any symmetric block cipher, including triple DES and AES. The most important modes are described briefly in the remainder of this section. Electronic Code Book Mode, ECB. The simplest way to proceed is using what is known as Electronic Codebook, ECB mode, in which plain text is handled B bits at a time, and each block of plain text is encrypted using the same key. The term codebook is used because for a given key, there is a unique ciphertext for every B block of plain text. Therefore, one can imagine a gigantic codebook in which there is an entry for every possible B-bit pattern plaintext, showing its corresponding ciphertext. With ECB, if the same B-bit block of plaintext appears more than once in the message, it is always producing the same ciphertext. Because of this, for lengthy messages, the ECB mode may not be secure. If the message is highly structured, it may be possible for a cryptanalyst to exploit these regularities. For example, if it is known that the message always starts out with a certain predefined field, then the cryptanalyst may have a number of known plaintext ciphertext pairs to work with. If the message has repetitive elements with a period of repetition, a multiple of B bits, then these elements can be identified by the analyst. This may help in the analysis or may provide an opportunity for substituting or rearranging blocks. To overcome the security deficiencies of ECB, We would like a technique in which the same plaintext block, if repeated, produces different ciphertext blocks. In the cipher block chaining (CBC) mode, the input to the encryption algorithm is the XOR of the current plaintext block and the preceding ciphertext block. The same key is used for each block. In effect, we have chained together the processing of the sequence of plaintext blocks. The input to the encryption function for each plaintext block bears no fixed relationship to the plaintext block. Therefore, repeating patterns of B bits are not exposed. For decryption, each cipher block is passed through the decryption algorithm. The result is XORed with the preceding ciphertext block to produce the plaintext block. To produce the first block of ciphertext, an initialization vector IV is XORed with the first block of plaintext. On decryption, the IV is XORed with the output of the decryption algorithm to recover the first block of plaintext. The IV must be known to both the sender and receiver. For maximum security, the IV should be protected as well as the key. This could be done by sending the IV using ECB encryption. One reason for protecting the IV is as follows. If an opponent is able to fool the receiver into using a different value for IV, then the opponent is able to invert selected bits in the first block of plaintext. It is possible to convert any block cipher into a stream cipher by using the cipher feedback mode, CFB. A stream cipher eliminates the need to pad a message to be an integral number of blocks. It also can operate in real time. Thus, if a character stream is being transmitted, each character can be encrypted and transmitted immediately using a character-oriented stream cipher. One desirable property of a stream cipher is that the ciphertext be of the same length as the plaintext. Thus, if 8-bit characters are being transmitted, each character should be encrypted using 8 bits. If more than 8 bits are used, transmission capacity is wasted. The figure depicts the CFB scheme. In the figure, it is assumed that the unit of transmission is S bits. A common value is S equals 8. As with CBC, the units of plaintext are chained together so that the ciphertext of any plaintext unit is a function of all the preceding plaintext. Although interest in the counter mode, CTR, has increased recently, with applications to ATM, asynchronous transfer mode network security, and IPsec IP security, this mode was proposed early on. The figure depicts the CTR mode. A counter equal to the plaintext block size is used. The only requirement stated is that the counter value must be different for each plaintext block that is encrypted. Typically, the counter is initialized to some value and then incremented by 1 for each subsequent block. Module 2B, where B is the block size. For encryption, the counter is encrypted and then XORed with the plaintext block to produce the ciphertext block. There is no chaining. For decryption, the same sequence of counter values is used, with each encrypted counter XORed with a ciphertext block to recover the corresponding plaintext block. So what are the advantages of CTR mode? So here we have a list of the following advantages. Hardware efficiency. Unlike the chaining modes, encryption or decryption in CTR mode can be done in parallel on multiple blocks of plaintext or ciphertext. For the chaining modes, the algorithm must complete the computation on one block before beginning on the next block. This limits the maximum throughput of the algorithm to the reciprocal of the time for one execution of the block encryption or decryption. In CTR mode, the throughput is only limited by the amount of parallelism that is achieved. Software efficiency. Similarly, because all of the opportunities for parallel execution in CTR mode, processors that support parallel features, such as aggressive pipelining, multiple instruction dispatch per clock cycle, a large number of registers, and SIMD instructions can be effectively utilized. Preprocessing. The execution of the underlying encryption algorithm does not depend on input of the plaintext or ciphertext. Therefore, if sufficient memory is available and security is maintained, preprocessing can be used to prepare the amount of encryption boxes that feed into the XOR functions. When the plaintext or ciphertext input is presented, then the only computation is a series of XORs. Such a strategy greatly enhances throughput. Random access. The ith block of plaintext or ciphertext can be processed in random access fashion. With the chaining modes, block CI cannot be computed until the I-1 prior block are computed. There may be applications in which a ciphertext is stored and it is desired to decrypt just one block. For such applications, the random access feature is attractive. For example, you could use this for reading a file. When a random read is performed, you could use this algorithm and just decrypt the part of the file that you need. Provable security. It can be shown that CTR is at least as secure as the other modes discussed in the section. Simplicity. Unlike ECB and CBC modes, CTR mode requires only the implementation of the encryption algorithm and not the decryption algorithm. This matters most when the decryption algorithm differs substantially from the encryption algorithm, as it does for AES. In addition, the decryption key scheduling need not be implemented. Summary. So here we have a summary talking about the symmetric encryption principles, symmetric block encryption algorithms, random and pseudo-random numbers, stream cipher and RC4, and then we went into the cipher block modes of operation. And those cipher modes, blocks of operation, you can understand them very easily, or much more easily, if you watch the Virginia University optional course material. They have lessons and they go over diagrams and pictures and explain it. So that would be another great input for your knowledge of this chapter. Okay, thanks for listening. Bye for now.